Hello, my name is Fiachra O'Connell, and this is a presentation on the junctionless transistor. The junctionless transistor was first successfully fabricated by Jean-Pierre Collinge at the Tyndall Research Institute, UCC. It was a modification of the traditional transistor in which the current doesn't flow through any p-n junction. The reason why this is so important to us is because transistors have become so small that they have reached a point where they can't get any smaller. Traditionally, processors have gotten progressively faster due to this year-on-year increase of transistor density described by Moore's law. With transistors unable to get any smaller, processor speeds will stagnate. The junctionless transistor provides an alternative way of speeding up processors by making the billions of transistors they are comprised of more efficient. The device works by having an incredibly small silicon nanowire tube that carries the current from source to drain. This channel is uniformly doped either in N-type or P-type, giving it an advantage over its MOSFET cousins, which include hard-to-manufacture sharp doping gradients. The current throughout the device is controlled by a gate on top of the silicon nanowire, which is separated by a gate oxide. In its on state, the current is allowed to flow freely through the silicon channel. However, as gate voltage is increased to above the threshold value, the current stops flowing. The increase in gate voltage acts like a clamp on a hosepipe, gradually restricting water flow until at some clamp pressure the water is unable to flow. In a junctionless transistor, this is known as the pinch-off voltage, and is what describes the device's off state. Even though it shows very similar electrical characteristics, the junctionless transistor holds many advantages over a traditional transistor, including its small leakage current, which is the current that flows when the device is in its off state, and the fact that it's much less affected by drain-induced barrier lowering, which is the effect where the threshold or pinch-off voltage is reduced as the drain-to-source voltage is increased, which can cause the device to turn on prematurely. The two main downfalls of the current junctionless transistor design are its incredibly high manufacturing costs and the lack of ability to manufacture in large quantities, both owing to the novel nature of the design. There are currently two frontrunners for variations of the device that could solve these problems in the future. These are the bulk planar junctionless transistor and the junctionless vertical MOSFET. Both of these incorporate technologies already used in junctioned transistors, and so these improvements have already been proven in industry, making their research lucrative to those trying to make the junctionless transistor economically viable. The bulk planar junctionless transistor improves on the design of the junctionless transistor by removing the buried oxide insulation that the silicon nanowire usually sits on, and instead replacing it with a bulk silicon well, which is doped oppositely to the channel. This is more in line with industry standards and allows the junctionless transistor to be more compatible with current CMOS technology. It also makes the device more scalable and cheaper to produce, which has granted the bulk planar junctionless transistor the lion's share of current research funding for junctionless transistors. The junctionless vertical MOSFET changes the design of the junctionless transistor significantly to include a vertical channel from source to drain, which is accompanied on either side by a gate. This gate structure allows for more rigid control of the current, and the shape of the channel contributes to a reduction in its parasitic resistance by almost 0.6 kiloohms per micrometer for any given gate length. The architecture of the junctionless vertical MOSFET allows for low-cost mass production. Its economical viability and performance benefits are very appealing, and this device should certainly be considered for further research in the future. In conclusion, the junctionless transistor is a device that has the potential to stop an entire industry from stagnating with its more efficient design than transistors of the past. Its electrical characteristics, which strongly resemble that of junctionless transistors, will make them easy to integrate, and their performance benefits will make them an obvious choice for continued research in the near future.